Good morning, everyone. It's awesome to see you guys in person. It's really great. I have to say, it has been probably almost 2 years since I gave a live lecture in front of people like this. So I'm very excited. Hopefully I'm not too rusty. So thanks for coming. It's a great pleasure. So we're going to be talking about Turing machines today. So this chapter this week is going to be about formally defining computation in its full generality. And let me do a quick terminology reminder. So we're going to be actually defining a new computational model. So remember that a computational model specifies for us what are the allowed information processing rules, what kind of instructions are allowed, what kind of instructions are not allowed. A computational model specifies that. And then a machine, a computer, or a program, or an algorithm is basically like an instantiation of the computational model. And what that really means is that it's a specific sequence of instructions that the model allows you to have. Right, and in our context, machine, computer, program, algorithm, these are synonyms, even though, in everyday life, when we use the word like machine or computer, we think of a physical device, really. But in 251, we don't really care about physical implementations, so we're going to be identifying the physical device with the mathematical representation, which specifies how the information is modified, transformed from the input to the output. Okay, so in this lecture, we're going to be talking about the Turing machine computational model and the machines, computers that is allowed by this model is called Turing machine. Okay? All right, so I made two assumptions in the DFA lecture when we started the DFA lecture. The first assumption I made is that, look, these wonderful machines, computers that you're using today, these are actually special kinds of machines. These are what we would call a universal machine. And the universal machine is such that it can actually be programmed to run any kind of an algorithm, any kind of a program, right? And we sort of take this concept for granted. We are used to it so much. But if you think about it, this is not actually a trivial concept. It's something that needs to be motivated. And I don't want you to just assume that this concept is trivial and, of course, we have universal machines. Let's try to imagine that we live in a world where this concept doesn't exist yet, and we'll try to build up to it. And I'll talk about it actually more in the next lecture. But for now, just imagine no universal machine, which means that basically for each task that you need to solve, you need a separate machine, okay? You need to go and buy a separate machine for each kind of task you want to do. And the second assumption is that for now, we're just looking at decision problems. Our focus will be on decision problems. Yes, no questions, kind of without loss of generality, as we discussed. Any computational problem kind of has an equivalent decision version to it, okay? Now, let me tell you the goal of this lecture. So, as I said, we're going to be talking about Turing machines. So in this lecture, what I want to do is define for you what a Turing machine is and tell you how it operates, how it does computation. And I want to make sure that we all understand what we're talking about when we say a Turing machine. And that's the goal of this lecture. Arguably, next lecture is going to be the more interesting lecture, because in the next lecture, we're going to be really diving into the implications of this definition. In particular, I'm going to be looking at the connection between computation and physics, computation and philosophy. I'm going to be talking about some of the historical context in which these ideas have arose. We're going to be talking about what was Turing's motivation when he was publishing his paper. How did he come up with his definition? What are the amazing implications of this definition? As well as how our understanding has evolved over time, right? So this paper is, not quite 100 years old, but, getting close to 100 years old now. And, of course, our understanding over time has deepened, has matured quite a bit. So how did it evolve, and what can we say this today that perhaps it would be hard for Alan Turing or others at the time to say? Okay, so we're going to talk about all this cool stuff next lecture, and should be fun. But today, as I said, it's going to be about defining the model. Let's make sure that we understand what we're talking about. Now, let me give you a very quick reminder about DFAs, and I don't want to spend too much time on this and bore you, but I do want to present DFAs in a slightly different manner to you, and to try to make it look a bit more like a Turing machine, as you'll see. So I'm going to imagine the DFA as the state diagram plus what I'll call an input tape where the input resides initially. Okay, so we're imagining that we have this tape that consists of cells. The input is on the tape starting at index 0. And once the input ends, the rest of the cells contain the blank symbol here. There is a tape head that starts at index 0. This is the symbol that you're currently reading, that you're processing, or the DFA is doing. And as you can guess, as usual, we start at Q0, the initial state. We read the symbol under the tape head. It's a 1. We take the appropriate transition. It takes us to Q1. Now the tape head goes 1 step to the right. We read the symbol 0, take the appropriate transition, go to Q2, and so on. So at every step, the tape head is moving 1 step to the right. The computation proceeds in this manner, and it stops when the tape head reaches for the first time a blank symbol, and that you can think of the stopping condition for the computation. And in this case, we stop at an accepting state, so the decision is an accept. Okay? So just a quick reminder here, and we'll see that a Turing machine looks pretty similar to this in this lecture. Let me also remind you that a deterministic finite automata model, this is nothing but some programming language that we're defining. Okay, so we just define a programming language with a restrictive syntax. The things that you can do is limited. It's a bunch of basically switch statements that you have. You can have as many as you want, and these switch statements basically correspond to the transition function of the DFA. Okay? And this also highlights once again that, when we're talking about a DFA, we talk about a machine, right? When we talk about a machine, we're just talking about a piece of code, okay? Not a physical machine. So a DFA, think of it as an algorithm that specifies, right, how the input is transformed into the output, in this case, whether it should be accepting or rejecting. Okay? So now we come here, we want to now define computation more generally, right? DFA, as we saw, is a restricted model of computation. And my question now to you will be, when we are defining computation, when we're trying to come up with a mathematical model, what kind of properties would you want from that model? Okay, what should you strive for? And you don't have to actually think about it in the context of computation, but whenever there's something that you have of interest that you want to understand better, and you're building a mathematical model for it, what are the properties that you should strive for in your mathematical model? What are some ideas? Yes? So one idea is determinism. So that's very specific to, of course, computation. And that's a good assumption to start with. But let's think more generally. Let's say we're not even defining what computation is. It's something else. What kind of general properties you may want to have? At the back. Read write. Again, this is a bit specific to computation. Can you give me more general things? Formalism, yes. So in formalism, we want a precise mathematical definition. In some sense, maybe that's my interpretation. But what are the properties of that? What properties would you want from that mathematical definition? Like runtime? Again, very specific to computation. Forget computation for a second.
Well, if you're defining something, you'd ideally like it to be well-defined.
Well-defined, yes, very good. So that's one thing. We want a...
Another nice property would be that you want the size of your model to be much smaller than the size of the thing you're trying to model.
I like that, so much less. So the way I'm going to interpret this is that it should be simple, right? It should be as simple as possible. When you're trying to understand something and you build a mathematical model, the simpler the better, of course, right? And that is something we have to strive for, because we want to reason about this thing. We want to prove theorems. And if it's a complicated definition, that will make our lives harder. But now, what else do we need? We want as simple as possible, but if you make it maybe too simple, then what might happen? What's a potential problem if you go too simple?
You might lose some information.
Yeah, so now you may not be accurately capturing what you're trying to capture, right? So the other thing is like, it has to be, in some sense, a correct definition that captures faithfully what you're trying to study. So one is that simplicity that we talked about. And in the context of computation, you know, when I want to say, well, it captures faithfully computation, I'm going to describe that as generality, because what we're trying to do here is really capture computation in its full generality, right? We don't want to like define a model like DFA that is just too simple and it doesn't capture computation. Okay, and you know, if you think about Alan Turing's work and Turing's definition of the Turing machine model, it's really, you know, combines these two things in the most beautiful way. You can say like simplicity, generality, these might actually work against each other, right? So it's not clear that you could get a simple definition that is general enough to capture all computation. But the Turing machine, the beauty of the Turing machine model is that it combines these things in the most elegant, beautiful way. It's as simple as you can really hope it to be, and it somehow amazingly captures computation in its full generality. Okay, so we're gonna see that. Now, as we are like building towards this definition, let me make a couple of observations as motivations for our definition. One observation is that when we're trying to like come up with a model for computation, the device, the computer here, should be a finite object, or in other words, the algorithm that describes this computer should be a finite object. And this is actually, I hope you agree, that a very reasonable restriction or assumption to make, because look, you know, we are finite creatures, we have only finite resources, so I don't know how to build an infinite object in this universe, okay? I mean, I think we can't do that. So, you know, of course, a computer should be finite. There's a nice quote by Kleene that I think like captures this very nicely. He said that an algorithm is a finite answer to an infinite number of questions. So as an example, think about like primality testing problem. So for each number n, you want to know whether it's prime or not. That's an infinite number of questions, right? For each number, you need to know, is it prime or not? Now, when you write an algorithm, let's say you write a Python code, is prime, to solve that computational problem, that's a few lines of code. That is a finite thing, a few lines of code that answers an infinite number of questions. For each natural number, it will tell you whether it's prime or not. So in this sense, an algorithm is a finite answer to an infinite number of questions. So that's the first observation. The second observation is that this computing device should have, in some sense, unbounded memory. And what I mean by that is that there's always more space to work on if needed. So think about yourself if you're doing some computation calculation. If I were to give you two numbers to multiply, and let's say they're two 10-digit numbers, then you might use, let's say, one piece of paper to do that computation. That's great. But now if I give you, 100-digit numbers, you'll need more paper to work on. If I give you million-digit numbers, you will need even more paper. And so if you need more paper, you should be allowed to use more paper. That makes sense. It would not make sense to like give an arbitrary upper bound like 10 pages and say like, hey, you can only have 10 pages whenever you're doing computation. Right, so this is the spirit of this. There's always more space to work on if needed, is also part of the observation that we have. Okay, so now I want to reach the definition of the Turing machine model, right? This is no secret. And now I can do this actually in a couple of different ways. I can approach this definition from in some sense, the left-hand side here. Imagine ourselves like living in the early 1900s. David Hilbert asks the Entscheidung problem, and people are thinking about formally defining like mathematical reasoning, and they need to now define what an algorithm is, what computation is. And if you are living at that time, how could you have come up with the definition of a Turing machine? And that is important to do. We want to do that and approach it from the left-hand side. But I could actually also approach it from the right-hand side and say, look, we are at 2022 right now. We have computers. We use computers all the time. You're taking this course, so you have actually some programming experience as well. You have some programming intuition. So I can actually appeal to your programming experience and programming intuition and motivate the definition of a Turing machine in that way. And I think actually when you do that, it becomes a bit more clear, or it's easier to understand perhaps what a Turing machine is and how it operates, because you're better able to sort of connect it to what you already know. So I want to do both, of course. I'm going to like approach this from both sides. In this lecture, we're going to do it from the right-hand side, okay, to make sure that we understand, how Turing machines work. And then next lecture will be more so about approaching from the left-hand side here and think about like, well, how would someone living at that time and how did Alan Turing specifically come up with this definition? Okay. All right, so now we want to come to the definition of a Turing machine. So you're trying to, define computation. And here's like a good picture, perhaps, given what we know, that we can draw. So we have the DFA model. They solve regular languages. Good, so we can draw that set, the set of regular languages. And then we can now draw a bigger set, right? And we know like 0 to the n, 1 to the n is not regular, so it's outside the set. Primality testing is not regular, it's outside the set. And we can now call this outer set maybe solvable with any computing device. And why can we do that? Well, we know like 0 to the n, 1 to the n, for example, we can't compute it, right? It's not like we don't know how to compute 0 to the n, 1 to the n. Here's like a Python function for this. I will call this like the two-finger algorithm for 0 to the n, 1 to the n. You have one finger on the first index, another finger on the last index. You check, I have 0 and a 1, good. Then you move in one index, 0, 1, 0, 1, 0, 1, and so on. And of course, nothing special about Python. You can write this in C if you prefer C. But yeah, so we can actually solve 0 to the n, 1 to the n. We can solve also is prime, right? Now let me ask you a question that might seem a bit strange at first, but I think it's actually a nice question to ask and think about. Can we define, or should we define, this set solvable with any computing device to mean, solvable with Python? Okay, so here's my question to you. Should we define computable to mean what is computable by a Python program? Okay, so let's think about this. What are some maybe potential issues with this kind of definition? Yeah.
You might not have unlimited memory.
Okay, you may not have unlimited memory. So let me actually talk about that. So is that true? Is the syntax of Python limiting you in terms of memory? Actually, no, right? Now, of course, the computer you run your Python program on, that might have limited memory. But the way you should imagine this is that, look, if I need to hook up more memory to it, I can hook up more memory. So, but important observation here is that it's not that Python syntax limits you. Like it doesn't say like, oh, you can't have more, you can't have a bigger number, you can't represent a bigger number, let's say. So that's okay.
I mean, you're basically bolting your definition onto this very ungainly, I don't know however many thousands of lines of code Python is. You're bolting your definition onto that specific implementation. And if someone else from an alien civilization were to come along and say, my definition of computable means it's computable by a Java program, now you have to come along and prove that these things are equivalent.
Oh, very good.
Basic things, it's a nightmare.
Yeah, so I mean, I think you sort of bring up 2 points, right? One point is like, Python, if aliens came and we said our definition of computation is Python, we should be embarrassed by that, I think. But also, like, in terms of, first of all, simplicity, like, I mean, it's not simple, all right? But you also bring up another thing, like, why not Java or something else? So let me bring that up. So why Python? Why not C, Java, or SML, or your favorite programming language? Well, in terms of its power, does it make a difference, actually, whether it's Python, C, Java, SML? Yeah. Yes, but let's assume that we don't know what Turing complete means, right? So what's a good way? I mean, I agree with you. You have the right idea. You have the right answer. But in terms of like convincing someone else, what would be a good way to convince someone else that this is the case without really talking about Turing completeness?
Well, there are a lot of these languages actually share a common ancestor language. Like a lot of Python imports are written in C. Java is based off of libraries that were based off of C.
Right. So if you go all the way down, I mean, to execute any kind of code, everything has to compile down to machine language, right? I mean, because the only thing the only instructions your computer knows how to execute is actually simple machine language instructions, and all these are higher level abstractions that actually all compile down to machine language. So that's one nice way to see that these are all equivalent.
You can spend / waste several weekends writing a Python compiler in C, a C compiler in Java.
Right.
No, sorry, not compiler, interpreter.
Yes.
In Java.
Indeed, like Python interpreter is written in C, right?
Yeah. Or you can waste a weekend writing one yourself.
Yeah.
To prove that they're all equivalent.
Yeah. But that's exactly right. You can like write interpreters or for one language and another language. You can do that absolutely. But I think like the best way to see this is that they all boil down to machine language. And then and let me ask you this though. In terms of its generality, do you think like let's say Python or any of these languages captures computation in its full generality? Who would say yes? Let's do a quick vote. Yes? Yeah, good number. Okay. No? Who says no? Okay, so it's about 50-50. So why would you say, let's say no?
I think quantum computers now have more capability than we do in the
So one objection is like quantum computers, are they like, do they have more power? And okay, so I don't want to give maybe too much away right now, but the real power of quantum computation comes when you think about computational complexity. In terms of actually computability, what you can compute and not, it doesn't seem to matter. But that's a good point. So now, I mean, it's a good point in the sense that I'm not talking about like, let's not worry about computational complexity considerations, and let's just think about what is computable and what is not computable. So my answer would be that in terms of like, is it general enough? I would say, I think so. I mean, I don't know for sure right now. I have to make that argument. But my intuition would be to say, well, I think so, because if I think about my programming experience, whenever I come up with a solution to a problem that I can express as an algorithm, as like high-level English instructions, I can always translate that into Python code. I never feel like, oh, I have an English algorithm solution, but the Python syntax was just too limiting and it didn't allow me to express what I had in Python. This doesn't happen, okay? And so it seems in that sense, at least, that it is general enough. But on the other hand, is it simple enough? And now we're talking about, okay, Python has like hundreds of pages of documentation. It doesn't even have a formal definition. But even if you go to something like, machine language, bytecode, that might have 10 pages. The definition might be like 10 pages long. And from a mathematical point of view, that's a no-go as a definition, okay? So no self-respecting mathematician is going to work with a 10-page definition. So we need something simpler than that. So what we want is a totally minimal programming language with the following properties. It can simulate, we want it to simulate simple bytecode. And if it can do that, then it can actually simulate, Python, C, so it can do whatever these other programming languages can do. But at the same time, we want it to be simple enough so that we can define it and reason about it rigorously, okay? And of course, this totally minimal programming language, this TM, really stands for Turing Machine, right? Defined by Alan Turing in 1936 when he was 23 years old. He didn't call it the Turing Machine. We now call it Turing Machine after him. And yeah, this is a good model for a PhD thesis. So if you want to write a PhD thesis, this is a good example to follow, I guess. All right, so let me now describe to you what the Turing Machine is. And given what you know, given your knowledge about deterministic finite automata, I think a good way to describe to you what a Turing machine is would be to say that it's really a DFA, think of a DFA, plus an infinite tape that the machine, that the finite state machine can use as working space, can use as memory, right? So the thing that we said about DFA is it has limited amount of memory, and that's the key limitation. Now we're gonna, remove that limitation and say, okay, you can use memory if you want. You have the tape, use all the cells, whatever cells you want, and That will be now our new model that we'll call Turing machine. So we have the tape, okay? So we're going to imagine the tape is infinite in two directions. It doesn't matter that it's infinite in two directions or infinite in one direction. Either way would be fine, but in terms of the definitions, it's a bit more convenient to imagine it's infinite in two directions. You have the input written on the tape starting at index 0, right? In this case, the input is AABA. And of course, all the other cells that don't contain the input contain the blank symbol. Our blank symbol is the square cup symbol. There's a tape pointer had initially at index 0, so you can see it's pointing to initially at index 0, and it can now move actually left or right, one step to the left or one step to the right. In the case of a DFA, at the beginning of the lecture, the way I showed you, it only moves right one step, right? But now it goes left or right. And maybe the most crucial property now is that, of course, it can read the tape head. You can read what's under the tape head, but crucially, you can now write to the tape on that location. Okay, you can change the contents of the tape, which now allows you to really use this tape as, in some sense, memory, right? So this is really the crucial aspect of, or the crucial difference between a Turing machine and a DFA. In some sense, a DFA, you can think of it as a read-only machine. It just reads the input. It can only read the input. But now we have a machine that's not read-only. It can read and write, and that's crucial. Now then, what are the sort of allowed instructions in some sense for a Turing machine? So we could define a Turing machine as a sequence of instructions where the allowed instructions look like this. So you have move the head left, that's one instruction. Move the head right, that's another instruction. Write a symbol A from the alphabet. If head is reading a symbol A, go to step, or line number J, halt and accept, and halt and reject. Okay, so then you can write a program, line by line, where each line basically is like an instruction like this. And you can think of a Turing machine in this manner if you would like to. That's completely fine. On the other hand, we want to keep the definition as simple as possible. So in that spirit, we're going to, sort of boil down all these different instructions into one single instruction. So a Turing machine actually is going to have one instruction only. And that instruction looks like the following. It's kind of what we've seen before in the context of DFA. It's a switch statement with a few extra components, a couple of extra components. So you're looking, of course, the letter under the tape head, and based on what that letter is, you're going to decide to take certain actions. One, first of all, if it's an A, right, say, maybe you decide you want to write B on that same location. Maybe then you want to move left. You have to decide whether you want to move left or right, and then which state now you want to go to, the new state. Okay, and then for each possible letter symbol that you can be reading, you have these specifications of what to do, what to write, which direction to go, and which state to go to. Now, if this was a DFA, we would not have this write statement, and we would not have this move, and it would be just the go-to statement here. Okay, so the difference between a DFA instruction and a Turing machine instruction is that in a Turing machine instruction, you also have the write and the move thing. Okay? Now, given this means that at each step of the computation, you have to write a new symbol to the cell under the tape head. You have to move the tape head left or right, and you have to go to a new state. Okay? Now, you might be like, hold on, why am I required to do these things? Well, let's say I don't want to change the symbol. What can I do? Write the same symbol, exactly, right? So this is not a restriction at all, actually. You can write the same symbol. What if we want to stay put? Get back, yeah.
You just simulate every step until you move. And
you do all those steps at once. Yes, but that actually changes the definition, I think, the model. So I want to, can I do it without changing the definition of the model? I think you have a good idea, but I guess, yeah, that's what I want.
Move left and right in the same.
Yeah, so move left then right? So I'm going to keep the same instruction set, and if I want to stay, well, I can go left, come right, and then I'm back, right? So that will be easy to do. And you don't want to change the state, but okay, so you can go to the same state. That's not a problem, okay? Good, so this is a description, and now, DFAs were simple enough such that, we could draw a state diagram representing the logic of a DFA, and similarly, Turing machines are simple enough so that we can actually, represent the logic of a Turing machine with a state diagram. And here is a state diagram now of a particular Turing machine, and this one has 1, 2, 3, 4, 5 states. Now let's inspect this state diagram and let's compare it to the state diagram of a DFA. So what kind of differences are you observing in this state diagram? Yeah.
You also see that there's left and rights on top of it.
Yeah, so you see, well, obviously, like the labels on the transitions are more complicated now. It's not just one symbol, but you have like 3 pieces of information there. Very good. What else do you see? What other difference? Yeah. Good. So you see the reject and accepting states, they're kind of sync states. There's no arrow leaving them. So what's an educated guess on what that really means? Yeah. Halt, exactly right. So what that really means is that once you reach one of these states, Q reject, Q accept, computation stops. That's the halting condition. And in this case, you accept, Q accept, and in this case, you reject, Q reject. Why is this the case? Well, in the case of a DFA, if you remember, the halting condition is that once you consume all the symbols one after the other and you hit this blank symbol, that's when you halt. Now, in the case of a Turing machine, of course, we don't want to halt once we reach a blank symbol. We want to use those blank areas as working memory, so we will want to actually keep going even if we do reach a blank symbol. So then what should be then the stopping condition for a Turing machine? Well, this is the way we do it. We just have these halting states. So Q accept is a halting state, Q reject is a halting state, and when we reach one of these states, that's when we halt at the computation. And now let's look at the transition function that you highlighted, right? So this is like, of course, very different from what we've seen at DFA. So what is the interpretation of this? So let's see, this arrow originates from Q0. So if you're in state Q0 and you read the symbol A, so the first symbol A you see here is the same as the one in the DFA, right? This is what you're reading. And then what this tells you, this transition tells you, is that once you read A, change it to the blank symbol and then move one step to the right. Okay, so let me write that up. If you're in state Q0 and you read the symbol A, then write the blank symbol on the tape at that location and then move one step to the right. And then after you do that, you reach the new state Q sub A. Okay? So once again, the first symbol here is what you read, the second symbol here is what you write, and the third symbol here is the direction that you will go to. Good, so hopefully now this is clear, that this picture, the state diagram. Let's do a simulation just to understand how the computation would proceed. Of course, just like in the DFA, we have Q0, and this is where we start. This is the starting state. And then the current the head position is index 0, and we are reading the symbol A. So we're going to be taking the appropriate transition, which will be in this case this one, because this is an A here, right? So we are reading an A, and this tells us change it to a blank symbol. Now, if you look at index 0 in the tape, you will see that it will change to a blank symbol. And then this also tells us to move one step to the right. So now if you look at the tape head, it will move one step to the right and come to index 1. After this, we arrive at the state Q sub A, and one step of the computation is complete. Okay, so this is one step, and all the steps are the same, right? So we're going to do the same thing now, just starting now in the Q sub A. We're currently reading, again, under index 1, A. This will mean that we have to take this transition because this is an A, this corresponds to an A. This is telling us change that into a blank symbol. So in this cell location, the A is going to be blank. And then move one step to the left. So then that takes us back to index 0. And then now we reach Q accept, and then the decision will be to accept. Okay? So you see, in this case, actually, the Turing machine did not even read the whole input. And that's okay, that's allowed. So a DFA has to read the whole input, but a Turing machine can make a decision without even reading the whole input. Let's do one more quickly, just so that we're all on the same page. So let's say now the input is B, A, and then we start at index 0. It's now as B, so we'll now take the B transition here, right, starting at Q0, take the one corresponding to B, turn that B into a blank symbol, so that's what happens, and then move one step to the right, and now it's pointing to index 1, and we arrive at Q sub B. Now at this point we are reading an A, so we take the appropriate transition, which is this one, because the symbol here is an A, turn that A into a blank symbol, so that's what happens here, and then move one step to the left, so we go back to index 0, and then that takes us now to Q reject, and then the decision is to reject. Okay? So this is how it operates, and once again I want to highlight to you that this is nothing but some programming language. And right, so this state diagram is completely equivalent to, let's say, writing it as like a usual piece of code as a bunch of switch statements, where the switch statements basically correspond to the transition functions here. Okay, so now here's a poll question for you. The machine accepts a string X if and only if. Okay, so let's see. So D is the clear winner here, which says basically the length of X should be at least 2, and the first two characters, the first two symbols, should be the same. And that's exactly correct. So let's reason through this a little bit, okay? So the first question maybe that you should look at is, what if, like, let's say the input string was of length 1. It just contained one symbol. Well, what would happen? Let's see. So if it was just one symbol, let's, without loss of generality, let's say it's an A, then you would read the A, you would come to Q sub A. That will take you one step to the right, the tape head. And then at that position, you're going to be reading a blank symbol, right? Because it's just one character long, the input. So then the blank will take you to Q reject. So you reject. And the similar thing happens if it was a B, you'd read a B, and then you read a blank symbol, that takes you to Q reject. What if the input is the empty string? Then what does the tape look like?
Oh, I just have a question.
Oh, sure.
So I was wondering whether you're ever allowed to have backwards arrows or whether they always have to go forward. Like, could you have QB going back to Q0?
QB going, yeah, of course, yes. The arrows you define how you want to define. So this is one particular Turing machine where the arrows are defined in this way, but you can draw your Turing machine any way you want. What is important here is that, just like in the DFA, right, what we said is that in a DFA model, let's say the alphabet is A and B, right, so the input alphabet is A and B. Then from each state, you need two arrows leaving it, one with labeled A and one with labeled B. In this case, what we need is that from each state, other than the Q reject and Q accept states, we will need 3 arrows leaving it because, well, we have A and B, but we also need to know what we need to do if we read the blank symbol. So we need that, but then where these transitions go to, this is up to you. This is your definition of the Turing machine. Okay, so now let me come back to my question, which was like, what happens when the input is the empty string? What's the tape like in that case? It's just the blank, like it's completely blank. So then what will happen, you will start at Q0 and you will immediately read blank, and that will just take you to Q reject. So this means that if the input is the empty string or if the input has length 1, we are rejecting. So we need the input to be of length at least 2. And then you can reason and say, well, if it has length at least 2 and the first 2 characters are the same, then it will accept, right? So the only way it accepts is, it reads an A and then it reads another A, it accepts. It reads a B and then it reads another B, it accepts. If it reads an A and then a B, reject. If it reads a B and then an A, rejects. Yeah?
Is there any special way we denote like the reject state, or is it just we should like name it some convention and then
The rejecting state, the naming convention, is that?
like for the accept state we have the double circle
Oh yeah, so right, so the double circle, I just drew the double circle just to make it like similar to a DFA, but there's no need for a double circle. Q accept is the accepting state, Q reject is the rejecting state. Yeah.
Do we have multiple accepting and rejecting states?
Very good. So can we have multiple accepting and rejecting states? Who has an answer to this question? Let's see, someone who's not maybe talked yet. Yeah? Yeah. Yeah, exactly, right? So suppose you had two accepting states. Well, did you really need two accepting states? You could have just merged them together into one accepting state, right? Because it doesn't matter. Once you reach an accepting state, computation stops, right? So in that sense, hopefully you see that it doesn't actually make sense or it's redundant to have more than one accepting state or more than one rejecting state. Yeah, at the back.
Is it possible to not reach an accepting or rejecting state? Like I know the state is sensitive, but what if
Very good. So yeah, exactly. So you're saying, like, is it possible for the Turing machine to not reach an accepting or rejecting state? And what do you guys think?
Yes.
Indeed, it is possible. So let me ask you this. In your programming experience, have you ever written an infinite loop? I'm sure every single one of you in this room has written an infinite loop, right? And this is exactly what that corresponds to. You don't reach an accepting or rejecting state, and it is possible indeed. A very good question. Very good question. Okay, so any other questions about this? Yeah.
What happens if you start with the empty character thing, and then have like X and Y?
Right, very good. So the question is, what if we, like at the index 0, we had an empty blank symbol, and then the input is written, let's say, AB, AB. This is not allowed. So the assumption is that in this model, the input always starts at index 0. And also, it's the case that you cannot put blank symbols within like the characters of the input, right? So the input starts at index 0, and it's like contiguous, right? So index 1 contains the second character, index 2 contains third character, and so on. So that's like the initial configuration that you need to have. That's the assumption. Yeah.
So this like absolute value of x symbol that's used in the poll, so that's the length of the string when it's initially fed in. Is that symbol defined throughout the computation as like the number of non-zero symbols, or is that just defined at the start and then
yeah.
and then it's mutable?
So the question is that, you know, in the poll we had this variable x, and we used absolute value sign to denote the length of x. And of course that makes sense, you know, that's like a well-defined notion, number of symbols in the input. Now the question is, like, what about as the computation proceeds, like, is there a corresponding notion of a length of whatever x might be, maybe corresponding to the contents of the tape? And really the answer is kind of no, right? Because as you're doing the computation now, there can be blank symbols in between like actual A and B, A's and B's. So then how do you define? So we don't have like a definition of, oh, it's the number of non-blank symbols. We don't use that notation, no.
You know how we're like going through and also changing the symbols as we go through? Is that like, what do we call kind of the result from like actually changing the symbols? Like, is that like the result of the computation?
Yeah, very good. So the question is, as we're going through and changing the symbols, you know, what can we consider as the result of the computation? So now in this case, as I said, we're just interested in, you know, solving decision problems. So we're just interested in, like, are we accepting or rejecting, and that we are considering as the result of the computation. But you can of course ask, what about, you know, solving more general computational problems, let's say function problems. Let's say you want to do multiplication, let's say, of two numbers, and you want to see the product of those two numbers. How would that work? And yes, there's a notion that we can define in Turing machines. So in that case, what you would want is that, of course, the Turing machine has the input, and then you do the computation, and at the end, you want the output to appear on the tape as, again, a contiguous block of symbols, and then everything else is blank. Okay, and that's, you know, considered the output. So we can define the notion of a Turing machine computing a more general computational problem, function problem, and, you know, the output string of the Turing machine is, you know, as I described it. Very good question. Yeah.
say, like string, what if we know that a certain DFA is already capable of solving a computational problem? Then we just ignore the state.
Very good. So I guess like the question is like, what if I had a DFA solution, right? In the DFA solution, I have my state diagram. I cannot just use that state diagram of DFA as a Turing machine state diagram because, well, there's this difference like Q reject is a sync state, Q accept is a sync state. And your question is, well, do I have to, why are you restricting me to do that? Well, this is a definition. And I mean, if you think about it, we have to kind of define, in some way, we have to define the notion of halting, right, in a Turing machine. And really, like, this is a good way to do it. And this is the way we're doing it as like sync states. And yes, these have to be sync states, which means that now, yes, you have to make actually a small modification to your DFA state diagram, which actually, great segue, because this is exactly what I want to say next, is like, here's a language, here's an exercise for you that I'm not going to do now, but please do this. So draw the state diagram of a Turing machine that accepts a string if and only if it starts and ends with the same bit. If you remember the DFA lecture, we drew a state diagram for of a DFA that solves this language, correct? So you know the logic behind how to solve this with a DFA. And so now what I would like you to do is translate this into a Turing machine state diagram. And here, since you know the logic of how to solve it, that's not going to be really the exercise. The point of the exercise here is to really understand the syntax of the Turing machine, getting comfortable with the transition functions of the Turing machine. And also, as you said, like you have to make sure that you're using the accepting and rejecting states properly. Okay, so this would be a nice little exercise. Yeah. So the question is, can I put multiple L's and R's here? And the answer is no, right? So at one step, we just allow one step of going left, one step going right. And if you need to go like multiple steps, then you would have to like have more transitions, more states, perhaps. Yeah, okay, so how can we implement left and right? So who has an idea about how to do that? At the very back. Yeah, you.
That is just like read and write, or like when you go right, you read and write the same thing, and then you go left, and then read and rewrite it.
I think you might need a new state if you want to do like a. Yeah, I think like a good way to do this is that you can imagine having one state, like some kind of a dummy state, and then you sort of go there left and then come back right, for example. Very good. All right, so let's go and do a formal definition of a Turing machine, because we talked about the high level what it is, but we should now see the formal definition. And yeah, luckily this will actually fit into one slide, just like the formal definition of DFA fit into one slide. And you'll see that the definitions are extremely close. The formal definitions are extremely close. Now we have a 7-tuple instead of a 5-tuple. But yeah, these are very similar. So Q is our old friend, the set of states, just like in the DFA. It's a finite non-empty set. Sigma is what we're going to call, in this case, an input alphabet. Okay, so this is the set of symbols used to create the input string. Now, the blank symbol, of course, should not be part of the input alphabet, because if blank symbol was part of the alphabet, that would kind of be confusing, right? Then in some sense, the whole tape, the infinite tape, would be the input, right? You wouldn't know which part is the input, which part is not the input. So we don't want to put the blank part of the input alphabet. Now, because of this distinction, we actually, in the Turing machine, have a second alphabet. This is capital gamma. And it's again a finite set. It contains everything in the input alphabet, sigma, but it also contains the blank symbol, and it can contain more symbols if you want to, if that's convenient for you. So this tape alphabet basically allows you to have more symbols if you would like to use it, if it's convenient. Though this is not really necessary. You could define the tape alphabet to be like sigma union the blank symbol and be done with it. But this definition does allow, gives some flexibility.
Wait, are you saying that, like, are those the only elements in gamma, or could there be other elements?
Yeah, exactly. So I'm saying there could be other elements in gamma.
Yeah, but are the other elements exclusively the blank?
No, so like that, yeah, that's what I'm saying. So it could be like you have the input alphabet is A and B. You have the blank symbol, and perhaps you also have like a hashtag symbol. You decide that in the gamma you want the hashtag symbol. And we'll see an example of that. All right, so then we have the delta function, the transition function, and it looks actually similar to the transition function of the DFA. Recall the transition function of a DFA is what? Delta, the signature is Q times sigma. Tell me which state you're in, tell me which symbol you're reading, and then the output is another state Q. Now you can see it's almost like Q times alphabet to Q, but you have two more pieces of information here, gamma and left and right. Now, first of all, with respect to gamma, why do we have gamma here and not sigma? Because we need to know how to transition, given any tape symbol, right? So it's not just for elements of sigma I need to know how to transition, but I need to know for any element of the tape alphabet how to transition. And then, as the output, okay, I need to know, of course, which state to go to, but a Turing machine has two more properties, two more things that it does. Well, first, it writes a new symbol to the tape under the tape head. This is the new symbol that you write. And then you go left or right. That's the direction that you go to. Yeah?
Shouldn't it not be going from Q cross gamma, but
right.
Q set minus Q after Q, right?
Yes, so the question is like, since Q accept and Q reject are sync states, technically there shouldn't be a definition for that. And you're right. So technically you can define it that way. I'm going to define it in this more general way to keep the syntax, clean here. And in some sense, yes, maybe you need to this forces you to define those transitions, but we don't care about them, let's say. That's one way to handle it. Okay, yeah.
If you decided to introduce new symbols into gamma, wouldn't you need to specify what the machine does to those symbols, even if you were at a state where you know that it would be impossible for you to be reading those symbols?
And yeah, so you are saying basically there could be a Turing machine such that you know that there will never be a situation where you're in that state Q and you read the symbol from gamma, and it's possible. It's hard to reason, of course, about these things, and it would be very difficult to make a definition which takes that into account, because then you're thinking about the logic of the Turing machine. So we don't care about it. We just specify it. Maybe it doesn't ever reach that configuration. That's fine, but we have to specify it. Okay. And then we have the initial state of Q0. We have the Q accept state, of course, the accepting state, and we have the rejecting state, Q reject. And here, Q accept, of course, should not be equal to Q reject, because that we don't know if we accept or reject. But it could be the case that Q0, let's say, is a Q accept or Q reject. So the initial state could be the accepting or rejecting state. That's allowed. Okay, so that's the formal definition of a Turing machine, all the pieces, very similar to a DFA. And then there's also a notion of Turing machine accepting a string, but actually I'm going to skip this and I'm going to let you go through it in the textbook yourself, the notion of a configuration. So you start with the initial configuration. At each step of the computation, you change configuration, and at the end you reach either an accepting configuration or a rejecting configuration. Okay, so let's now quickly discuss the similarities and differences between DFAs and Turing machines. So one is that a DFA, of course, does not have access to tape cells that don't contain the input, doesn't have access to unbounded memory. DFA's tape head can only, move right, as we discussed. A DFA can't write to the tape, and it wouldn't matter if it could write to the tape, because if you can only move right, then there's no way for you to go back and read what you wrote. And a DFA can have more than one accepting state, as we discussed. Like the condition for halting is, of course, different. A DFA halts once the input symbols are read. A Turing machine might loop forever. This is where we have discussed this already. So there are three possibilities. When a Turing machine gets an input X, there are three possible things that can happen. Either the Turing machine will accept that string X, it will either reject that string X, or it will get in an infinite loop. It will get stuck in a loop forever. Okay, and this is a crucial difference between Turing machines and DFAs. Okay, so in the context of a DFA, we define the notion of a regular language. These are languages that can be solved by a DFA. In the context of Turing machines, these are going to be called decidable languages. So let me quickly give you some definitions here. This will be completely, in some sense, analogous to the definitions we had in the regular languages case. Right, first, in the context of regular languages, we define the notion of a DFA solving a language. In the context here, we're going to define the notion of a Turing machine solving a language, and it's completely the same definition, like word for word, except that you change TM to a DFA, basically. So M be a Turing machine, L be a language. We say that M solves or decides the language L. If exactly what you expect, if W is in the language, then we want that M accepts W, and if W is not in the language, then we want that M rejects W, right? And as I said, this is exactly the same definition that I showed you in the DFA lecture. It's just that I changed this DFA to TM. The same notion of solving. Now, some Turing machines, as we said, can loop forever on certain inputs. We kind of don't like those kinds of Turing machines. They're buggy Turing machines. So Turing machines that are not buggy in that sense are called decider Turing machines. So a decider Turing machine is a Turing machine that halts, either accepts or rejects on all inputs. And observe that, of course, if you have a Turing machine M that solves, that decides some language L, it's necessarily a decider Turing machine. Because as you can see from the condition, for every input, whether it's in the language or not in the language, it halts and accepts or rejects. And finally, like the analogous notion of a regular language is a decidable language. So if you have a language that can be solved by a Turing machine, that is a decidable language. That's called a decidable language. Okay, now with these definitions at hand, we can ask some big questions and say, okay, is the set of regular languages the same as the set of decidable languages? Right? Are Turing machines and DFAs equivalent in power? And of course, the other question still remains, which is that, is Turing machine the right model of computation? Did we capture computation in its full generality? So now to convince you, well, I mean, our intuition, of course, is that regular languages are not the same as decidable languages. To convince you that this is the case, what can I do? Yeah, come up with a Turing machine that solves a non-regular language. And what is our favorite non-regular language? 0 to the n, 1 to the n, right? So let's come up with a Turing machine that decides 0 to the n, 1 to the n. Here is the state diagram of that machine. You don't have to parse this. Don't worry about the details here. One thing I'll point out is that the input alphabet is 0, 1, and the tape alphabet now is 0, 1, hashtag, and the blank symbol, okay? And I'm going to describe the logic of this, actually, by describing to you how this operates on the tape head. So I'm going to use one higher level of abstraction here. So let me describe to you how this state diagram, the logic here, what it implies in the tape. So we start, so the input here is going to be 4 zeros followed by 1, 0, 1, 1. We start initially at index 0, which points to 0. At this case, the Turing machine, if it sees a 1, it will reject, right? It starts with a 1, that's not good. If it sees a blank, then we have the empty string, then it's okay with that. If it sees a 0, it's okay with that. And if it sees a 0, it's actually going to turn this. I'm going to cross it off with the hashtag symbol. I'm going to write hashtag. And then I have a little subroutine, like 2, 3 states, that basically takes you all the way to the end of the tape, all the way to the end of the input, I should say. So it will have a loop here, go right, right, right. And as I'm going right, I'm writing. Whatever I'm reading, I'm going to write the same symbol. Go right, 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 until I hit the blank symbol, and then go one step now to the left. Now here I want to see a 1. If I see a 0, I reject. If I see a 1, I'm happy. I cross it off, hashtag symbol, and then there's a little subroutine that takes me all the way to the left now. Go left, 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 until I hit the hashtag symbol. Count one step to the right. Want to see a 0 here? If it's not a 0, reject. If it's a 0, cross it off. Go right, 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 right. Hit a hashtag symbol. Come one step to the left. If you don't see a 1 here, reject. You see a 1, you're happy. Cross it off with a hashtag symbol. Go left, 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 left. Come back, the same thing. And then here, at this point, when it sees the 0, it was supposed to see a 1. It will say, no, that's not good. Reject immediately at that point. Okay? So that's kind of how it works. Now, we still have this question, is the Turing machine the right computational model? I'm going to really go into this more so in the next lecture, but I want to say just one thing to finish the lecture off. I want to just say some quick observations about this, and then go deeper next lecture. So here, to understand the power of a Turing machine model, really, the trick is to build up its power in some sense, layer by layer, building up, smaller, larger and larger subroutines, and more complicated, useful subroutines. So one thing you can do is, as I said, kind of describe it in the previous example, you can write a little subroutine, 2-3 states, that accomplishes this task of moving right or left until you encounter a blank symbol. You can actually shift an entire string one cell to the right. So you can take like x1 to xn and just shift it one cell to the right. You can write a subroutine for this yourself as an exercise if you want. You can then convert a string like x1 to xn into like one where you have blank symbols in between, and that can be helpful potentially, having that space. And you can use the previous subroutine to accomplish this, right? You can take sort of x1 to xn shifted one by one, then take x2 to xn shifted by one, sort of kind of like that thing. You can now simulate a bigger gamma with just 0, 1 and the blank symbol. And in fact, you can imagine that the third subroutine could be useful because you can now maybe imagine treating two consecutive cells as like containing one symbol, and that could give you a notion of having a larger alphabet in some sense. That's kind of like a trick that you could use. You can have like a larger alphabet with like marked symbols, marked cells. So in the previous example, I used the hashtag symbol to like cross off something. But if you wanted to remember, for example, what symbol it was that I crossed off, well, you can create these marked symbols, 0 marked, 1 marked, and use those instead. And you can copy a stretch of tape between two marked cells into another part. You can go on like this. There's a notion of like a two-tape Turing machine. So you could imagine a model of computation that allows for 2 or 3 or 4 tapes or k number of tapes, each having its own tape head, and you imagine doing computation like that. It turns out, you can prove this, that any k-tape Turing machine can be simulated by a single tape Turing machine. And you can start building up, implement basic data structures, simulate random access memory, and so on and so forth, until you start simulating actually assembly language. And the point that I want to make here is that you can actually prove this rigorously if you wanted to. You wouldn't want to, of course. This would be like, Russell and Whitehead, like proving 1 + 1 = 2 in 100 pages. This will be analogous to that. But you can do this. This is a theorem. This is a fact. Right? So a theorem, any language that can be computed in your favorite programming language can be actually decided by a Turing machine. Right? So we wanted to come up with a totally minimal programming language that can simulate simple bytecode, that is simple enough to define and reason about mathematically rigorously. So we have done this successfully. I hope you sort of somewhat convinced. But yeah, so this question still remains, and this will be one of the focus points of the next lecture. Is the Turing machine the right definition? Is it possible that there is something outside of Turing machine decidable that we could solve perhaps with some other kind of computing device? So that's what we're going to be looking at next lecture. So the story continues next one. Thank you.